All right, let's get straight into it. Today, we are diving deep into something that can seriously make or break your grade, a single, high-stakes 12-mark exam question. We're going to pull apart a real question from an AQA GCSE Chemistry paper, piece by piece, to show you exactly how to lock in every single one of those marks. Let's do this.
So, the big question is, how do you actually do it? How do you make sure none of those precious marks slip through your fingers? It's not just about knowing the science, it's about knowing the rules of the game. It's about figuring out precisely what the examiner is looking for, using their exact language, and laying out your answer just right. Today, we're using the official mark scheme as our secret key to unlock all 12 marks. So what are we looking at today? We're zeroing in on question 07 from a higher tier paper. It's a perfect example, really, because it tests so many different skills. You've got reaction profiles, fuel cells, scientific models, and it all wraps up with a pretty meaty calculation. We're going to walk through every single part, and for each one, we'll look at the exact answers from the official mark scheme.
Okay, let's jump right in with the first part of the question. This bit is all about having a sharp eye for detail and spotting a couple of very common and very costly mistakes. So, the paper gives you this diagram. It's supposed to be a reaction profile for hydrogen and oxygen reacting, drawn by a student. Now, at first glance, you might think, okay, that looks about right. But is it? The question wants us to play detective here, because a couple of things are definitely not quite right. And here's the question itself. The student made 2 errors when drawing the reaction profile. Describe the 2 errors. 2 marks are up for grabs here, which is a big clue. We need to find 2 specific, distinct mistakes. Let's see what the mark scheme says.
And here they are, the 2 big mistakes. First off, that activation energy arrow. It's just plain wrong. It should always go from the reactant's energy level up to the peak of the curve. This student's drawn it from the products. And the second thing? This reaction is exothermic. It gives out energy. That means the products have to end up with less energy than you started with. So that product line should be lower than the reactant line. The student has accidentally drawn an endothermic profile.
Okay, moving on. Let's see how this exact reaction applies to the real world. We're now shifting into talking about hydrogen fuel cells, which is a huge topic in energy and a big part of the conversation about the future of cars. So, the next question puts 2 technologies head-to-head, hydrogen fuel cells versus the rechargeable batteries you see in most electric cars today. It's asking for 2 advantages of using hydrogen. Again, it's 2 marks, so they're looking for 2 clear points. And this is where things get interesting, because the mark scheme actually gives you a bunch of correct answers to choose from. You could talk about the environment, no toxic chemicals to get rid of. Or you could go for a practicality. They're way faster to refuel. You could also say you can travel further on a full tank. Or another great point is that they don't degrade over time like rechargeable batteries do. Any 2 of those, and you've got full marks. You've got options.
All right, next up, a quick 1-marker. This one's a straight-up test of your chemistry knowledge. Write a half equation for one of these reactions. Simple as that.
And look at this! Once again, you've got choices. The mark scheme is pretty generous. The top 2 are for what happens in acidic conditions, and the bottom 2 are for alkaline conditions. You only had to write down one of these 4 to bag the mark. So you don't even need to have all of them memorized, which is nice. All right, time to switch gears a bit. The question is taking a turn away from energy and equations, and now we're looking at the particle model of matter and some of the real-world, practical headaches of actually using hydrogen as a fuel.
So for the next part, they show you this picture. It's that classic dots-in-a-box model for a gas that we've all seen a million times. But here's the thing about models, right? They're useful, but they're never the full story. They always have limitations. And that's exactly what the question asks next. Give 2 limitations of this simple particle model for hydrogen gas. So what's wrong with this picture? What is it not showing us? They want 2 things for 2 marks.
And wow, check this out. The mark scheme gives you 6 possible things you could have said. For starters, hydrogen is H2, not just H atoms. So where are the molecules? Also, the particles are not just little solid spheres. And, this is a big one, for a gas, they're not moving. They're just sitting there, but they should be whizzing around. Any 2 from this list, and you're golden.
Okay, another 1-mark question, and this one's all about a real-world problem. Hydrogen is a gas, which means it takes up a ton of space. That's a huge issue for cars. So the question is, how do you solve that? How can you reduce the volume?
Well, the mark scheme gives us 3 great options. The most obvious one, squeeze it. Store it under really high pressure. Or you could get it super, super cold until it turns into a liquid, which is much denser. And then there's a slightly fancier answer. You could trap the gas in a solid material. Any one of those gets you the mark.
Okay, deep breaths, everyone. We've made it to the final boss of this question, the 4-mark multi-step calculation. This is where a lot of people might panic, but honestly, you don't have to. The secret is just to stay calm and take it one logical step at a time.
So here's what they're asking. We need to figure out the volume of hydrogen gas for a 100-kilometer trip, and they give us all the puzzle pieces we need. First, the total energy required is 58 megajoules. Second, we know how much energy 1 mole of hydrogen gives off. That's 290 kilojoules. And third, we know how much space 1 mole of gas takes up, 24 cubic decimeters.
Let's build our answer. Step 1, and this is super important, watch your units. They give you energy in megajoules times kilojoules. That's a classic trap. So first things first, we convert 58 megajoules into 58,000 kilojoules. Now we're talking the same language. Okay, step 2, how many moles do we actually need? We just divide the total energy we need by the energy we get per mole. So 58,000 divided by 290 gives us a nice round 200 moles. Almost there. Step 3, find the volume. We've got 200 moles, and we know each one takes up 24 cubic decimeters, so we just multiply those two together. And bingo! Our final answer is 4,800 cubic decimeters. And you see, by showing all your working like this, step by step, you're practically guaranteeing yourself marks along the way. Even if you trip up on the final bit of maths, you've already scored points for the conversion and for calculating the moles. That is so crucial on these big calculation questions.
So let's wrap this up. What are the big takeaways here? Number 1, read the question. Like, really read it and pull out the data. Number 2, use the right words. Be scientific, be concise, be precise. Number 3, with any maths, show you're working. Every single step. Don't just write down the answer. And number 4, remember that sometimes there's more than one right answer, so having a few up your sleeve is always a fantastic idea.
And there you have it, one 12-mark question completely broken down from start to finish. So I'll leave you with this to think about. We just walked through the process together. We've seen exactly what the examiners want to see. The real question is, how are you going to use this same systematic approach on the next big question you face? Because mastering that, well, that's how you win at exams.